Hey everyone, this is the fourth video in our series on electrochemistry. Moving forward into the notion of voltage and equilibrium, this connects everything back to what we have been doing in class, both with equilibrium as well as with spontaneity. What you'll notice, what you do remember before, right, is that delta G, the spontaneity, is equal to minus RT ln K. Well, a simple rearrangement of these two equations gives us the second equation here. So another way to think about it is a reaction that is highly spontaneous will also have a very large K. If it is a very large K, that results in a very large voltage. Doesn't it all fit together well? Large negative delta G, which is, the voltage potential here, right, makes it spontaneous. And another piece to this puzzle which fits in extremely consistently is the K. Large K, which means it lies very far to the right, would mean it is a spontaneous reaction, giving you a large voltage potential. It all works in unison. These are the same values that you've seen before. R is 8.314 because we're talking about energy, remember. T, temperature in Kelvin. N, the number of moles of electrons transferred. And F, the same Faraday's constant as above. One more definition I think we need to add to this before we launch into voltaic cells is the voltage definition of 1 volt is also defined as 1 joule of energy per coulomb of charge. I'll say that one more time in a different way. For two electrodes that differ by 1 volt of potential, 1 joule of energy is released for every coulomb of charge that moves between them. Galvanic cells. Galvanic cells are the fancy word for batteries. Yay. As you know, batteries are spontaneous things. We use them to drive non-spontaneous things. When I want to use my electric toothbrush, I put batteries in them because using my electric toothbrush means work has to be done. Where does that energy come from? It comes from the batteries. The energy from the batteries is used to do work. This is why joules of work and joules of energy have the same unit. Work and energy are synonymous. Work is energy being put to use. When I look at this cell, I want to point out a couple of different things. Notice that I have two electrodes, electrode 1 and electrode 2. Now, these two electrodes are in different chambers. This represents chambers. This could be two separate beakers, or it could be two chambers that are connected by a salt bridge, which is something that allows certain materials to flow in back and forth between. We'll get back to that in a moment. But a battery, most simply, are two separate chambers in which one chamber will undergo oxidation paired with reduction. When I look at this particular battery, what I notice is that the zinc is going from the neutral solid zinc and it's becoming zinc 2 positive. The zinc is losing electrons. Notice the arrow. The arrow is showing the electrons moving from left to right over into the chamber on the right. As this solid strip of zinc, right, loses electrons, they travel through the wire into the copper electrode. The copper electrode gains an excess of negativity from the electrons. When the copper ions floating in solution hit the electrode, they gain the electrons that are building up on the electrode. You could also envision this negative electrode pulling even some of these ions toward them. Because they're negative, this is positive. Let's look at the equation above. Notice that the zinc starts out neutral and the copper ion is the other reactant. The other reactant is not the copper electrode. This copper electrode is, in fact, notice it's a product. So this copper electrode is actually serving not as a reactant, but instead simply as a place for the copper 2 ion to gain electrons. One could even replace this electrode with an entirely different substance. The important part about it is that it's accumulating the electrons. The electron is gained into the copper. This particular electrode actually gets bigger as the copper deposits on it, and this particular electrode is actually going to start to degrade and get smaller as the zinc becomes aqueous zinc ions. The other essential part of this is what's called a salt bridge. Notice that the salt bridge is going to span the two chambers. These two chambers will the electrons will only flow for so long unless we have what's called a salt bridge between them. What the salt bridge is going to allow us to do is equalize the charge buildup, or actually reverse the charge buildup that's happening in these chambers. Our next video is going to get into a little bit more of the details on that. One final thing, electron flow is defined as opposite direction of current. I know that's a little bit counterintuitive, but that's how physicists have decided to do it, so you can blame them.